Now, up to this point, we've only been talking about cases where you just have one gas present. What if you've got a mixture of gases? It's a homogeneous mixture, as we talked about at the beginning. But what if we've got two or three gases in there and you're able to measure maybe the total pressure, but how do we figure out what contributions are coming from each gas, how that works for gases, and how we relate variables in the ideal gas law? Well, we can do this using something that's known as Dalton's law of partial pressures. This is actually the same John Dalton who postulated those four postulates of the atom back in chapter 2. And his law of partial pressures essentially just states that the total pressure of a mixture of gases equals the sum of the pressures that each gas would exert if it were present alone. What does this mean and why does this make sense? Well, essentially, remember that gases, the molecules are far away from each other. They act as if they're totally isolated, as if there's nothing else around. And so even if you have a mixture of gases, those gas molecules still act as if there's nothing else around. And so the pressure that they exert is going to be the same regardless of whether there was another gas present or not. So the total pressure of the system is just going to be the sum of the pressures of the individual gases. And so we can write this as pressure total is just pressure 1 plus pressure 2 plus pressure 3. Okay, so then how do we relate this to the ideal gas law? Well, we can rearrange the ideal gas law to solve for pressure and say that it's just, well, nRT over V. But assuming that the temperature of the system remains constant, so the temperature of one gas is the same as the temperature of another gas, is the same as the temperature of the third gas that's in the system, and that the volume of the container that they're in is constant, then we can we can put the gas constant, temperature, and volume all in parentheses because we can say those are a constant value, and RT over V is the same regardless of the gas that we're talking about. So the only difference is the number of moles of each gas, and we can relate the total pressure. We can substitute this in for the individual pressures and relate the total pressure directly to the individual number of moles. That's the only difference between the different gases, where the RT over V is the same regardless of the gas. So let's do an example of this. Let's say you have a container whose volume is 12.4 liters, and you've got 12.4 grams of helium, 15.2 grams of argon, and 2 grams of hydrogen gas. And the temperature for the whole system is exactly 17.3 degrees Celsius. What is the partial pressure of each gas? And what is the total pressure in the container? Well, we can start out just by figuring out the individual pressures of each gas. We're given a volume, so we know V. We're given a temperature, so we know T. R is always going to be just a gas constant, so we can look that up. And then we're given a mass, which we can convert to moles using the molar mass. So we know N, T, and V, and of course R. So we can then solve for P for each of the individual cases. Now, what will be simplest here is whatever the quantity RT over V, that quantity is going to be the same for all of the gases. So we can just solve for that. And then the only difference in terms of the different pressures is going to be the number of moles for the individual number of gases. So let's work our way through this. We can first rearrange this and say, well, the partial pressure of helium is just the number of moles of helium times RT over V. And the same thing for argon and hydrogen. Volume, as we mentioned, 12.4 liters. The temperature, we convert that to Kelvin, and we'll choose R as being the 0.08206 liter atmospheres per mole Kelvin. Here, in this case, we could have chosen a different one as well if we wanted to report the pressures in terms of torr or pascals, but here we just choose the standard one for R. So if we go through this, we just first calculate the number of moles of helium, just using the molar mass of helium, and we come out with 3.0977 moles of helium, and we can substitute this into the equation, we now just substitute in all of these values into the equation, value for R, value for T, value for volume, and then the number of moles, and we come out with 5.96 atmospheres for the pressure of helium. Now we can do that exact same process for the other two gases. So we first have to figure out the number of moles of argon that we do with its molar mass, and then substitute that into the equation just as previously. So you notice that nothing has changed in the equation except for the number of moles. You multiply this through and we come out with 0.731 atmospheres. Then you do the same thing for hydrogen. 2 grams divided by 2.02 grams per mole. We come out with 0.9901 moles of hydrogen. The same equation where the only thing has changed is the number of moles. We could have just calculated this quantity, RT over V, and then known what it was, and then substitute that in, just multiply it by the number of moles for each of them. In this case, when we multiply through, we come out with 1.90 atmospheres for hydrogen. So now we have figured out the partial pressure for each gas in this system, just doing standard calculations using the ideal gas law. So what's the total pressure for this container? Well, it's simply the sum of the partial pressures. So it's simply the sum of those 3 individual pressures. We add all of those together, sum them, follow some significant figure rules, and we come out with 8.59 atmospheres for the total pressure of the system. That's essentially just how we would use this to calculate partial pressures and total pressure. Now, while we're on this discussion, however, there is one other factor that's worth mentioning. That's something known as the mole fraction. So the mole fraction is given the symbol X, and the mole fraction itself is simply the number of moles of any gas over the total number of moles that are present. Now, this is also, because of the previous relationships, this is also equal to the partial pressure divided by the total pressure. Because that's directly related to the number of moles, that relationship holds then, where the mole fraction is just the number of moles of the gas you're interested in over the total number of moles, or it's the partial pressure of the gas divided by the total pressure. So we can use mole fraction to help us when we're discussing the amounts of gas that are present. So let's just take another example here. So dry air is composed of 78.1 mole percent nitrogen, 20.9 mole percent oxygen, 0.934 mole percent argon, and 0.033 mole percent carbon dioxide. If a standard sample of dry air has an atmospheric pressure of 749 torr, what is the partial pressure of oxygen in the sample? So we were given the total pressure, and we're given some mole percents. So here, let's just work through this. What is mole percent and how do we relate it to things? Well, mole percent is actually just, it's the number of moles of the gas you're interested in over the total number of moles times 100%. So it's simply the mole fraction times 100%. So mole percent here is simply, as I've listed here, N1 over the total number of moles times 100%, or that's, since N1 over NT is the mole fraction, then mole percent is just the mole fraction times 100%. So if we take, if we solve this for the mole fraction, we can get mole percent simply divided by 100%. So for oxygen here, which is what we're interested in, it's simply 20.9% divided by 100%. So we get 0.209 is the mole fraction for oxygen. Now I know from the above equation that the mole fraction is equal to not just the ratio of the moles, but the ratio of the pressure. So partial pressure over the total pressure. Well, I've just figured out the mole fraction, and I have been given the total pressure, 749. So all I need to do is solve for the partial pressure then. So PO2 over pressure total is equal to the mole fraction of O2. So we can rearrange that to solve for the partial pressure of O2 is the mole fraction times the total pressure. I have the mole fraction, I have the total pressure. I multiply those two together and I come out then with the partial pressure of oxygen being 157 torr. That's an example of how we would use partial pressures, how we would use mole fraction to be able to isolate and figure out certain amounts or parts of a mixture of gases.